Our second speaker is Dr. Anthony Wagner from the Department of Psychology at Stanford University. He's been doing a lot of interesting work on fMRI of memory and deception that I'll talk about today.
Thanks, Dan, and thanks to the organizers for the invitation to participate here today. My task, as I understand it, is to talk about possible mind reading as it surrounds memory, and so that'll be the focus of my 15 minutes. Along the way, I'll likely say a few things that interact with Stephen's presentation. So this question about whether neuroscience can help us in the area of memory has already been raised in a number of the earlier talks. Judge Fletcher, Hank made reference to the notion of, well, might neuroscience one day be able to tell us or allow us to sort of read out from somebody's brain whether or not an individual encountered a relevant person, place, or thing. I don't have necessarily an agenda here in my sort of attack on this question. I'd like to think I'm somewhat of a sort of just a neutral sort of assessor. We all have, I guess, our biases, but a neutral assessor. I came to this question partly through participation in the MacArthur Law and Neuroscience Project, and partly through this particular case. A number of folks in the room undoubtedly sort of encountered this in the Times and other press surrounding it. And there's a forensics lab in Mumbai, India, that uses scalp EEG to, in essence, read out from suspects whether or not they have neural signatures of guilty knowledge, whether they have neural markers or evidence that they were present or participated in some crime. And in this particular case, I think it came to the international community's attention because the individual was convicted of murder. And if you read the judge's transcript, it's trial by magistrate, I understand, that the neuroscience data heavily weighed on his decision-making. So we thinking that fMRI is likely the direction that future neuroscience methods might go, we simply wanted to sort of ask, okay, under very controlled laboratory settings, how well does fMRI do in addressing a number of core questions? So what I'm going to describe today is a project or two experiments that were supported by the MacArthur Law and Neuroscience Project in collaboration with Hank and my postdoc, Jesse Rissman, who's a new faculty member at UCLA, and this is heavily Jesse's work. So we sought to address a number of questions, those that I'll comment on. Can an fMRI-based approach decode subjective memory states? That is, whether or not a person is perceiving a stimulus as having been encountered or not. Can fMRI decode a person's true experiential history? This is often, I think, what the court will really care about, or the law will care about for items perceived as old. Can brain data be used to distinguish actual experience from false memory? And for items that are perceived as novel, can we nevertheless read out those that had been encountered, but perhaps and find a neural signature of memory that's perhaps outside of awareness? And there's a lot of sort of foundational cognitive neuroscience work, including work by Larry and Dan's labs, bearing on a number of these sort of basic science questions. Final question, can fMRI decode true experiential history even when memory is not directly probed? That is, can you read out from somebody's brains whether or not they encountered a stimulus or not, even if you're not asking them to reflect on their memories, to reflect on their past experience? And then I'll make a passing comment about the relationship between memory and lie detection. Okay, so let me just tell you the very highly controlled lab-based paradigm that we started with. Subjects come into the lab and they're presented individual faces one at a time, and they know they're in a memory experiment in this study, and they encounter the faces and they're trying to encode them for a later memory test. They're doing this outside of the scanner. They're just encountering the stimuli. And then following the study phase, there's about a 20-minute lag or so, and then subjects are brought into the MR scanner and they undergo functional MRI, which provides an indirect measure of neural responses. And participants are presented the stimuli that they encountered during the study phase and a bunch of novel foils. And during this test here, they're asked to indicate whether or not they recognize the faces having been previously encountered, having been studied. And so this, the interaction or the combination of the true objective status of an item and then the subject's sort of memory perception gets us four different kinds of stimuli. There are studied items that the person perceives as old. They actually are experiencing, recognizing the stimulus as having been encountered. These are hits. There are studied items that the person does not perceive as old or below their decision criterion. These are misses. So they call them new. They're non-studied items that the person correctly perceives as novel, correct rejections, non-studied items that the person has a false recognition of. They believe that they encountered the face even though they hadn't. The approach that we used, and the reason we adopt this approach, is to address one of the questions that was raised earlier by Larry Squire. The approach that we used is to use machine learning techniques that allow us to take, for every one of these test probes here, we have a volume of brain data, a measure of, in essence, the neural response to each of these test probes. We can take a subset of our data, volumes of brain data or distributed brain patterns associated with various test trials, and we can train up a classifier on a subset of these to try to discriminate between the two conditions, such as recognized, when a person is recognizing the stimulus versus perceiving it as novel. And then we can take, by training up this classifier, we now have this trained classifier, we can take a test pattern that hasn't been used to train the classifier. We can have the classifier now interpret that pattern and make a probabilistic statement. Well, the pattern looks more like, in this particular example, like the person is in this state of recognition versus this state of perceiving a stimulus as novel. And if this probability is greater than 0.5 on one side or the other, we'll state that the classifier interpreted that brain pattern as indicating that the person's brain state was in state 1 versus state 2. This approach has a number of advantages in terms of possible legal relevance, in that you can perform the data analysis at the individual subject level as opposed to the group level, and also at the individual trial level. You're getting a probabilistic statement, or you're getting a statement about a particular moment in the brain state in terms of how it relates to say, two different possible sort of mental categories. So in this first study, we started by seeing if we can discriminate or detect old stimuli that are recognized as old versus new stimuli that are perceived as novel, so hits versus correct rejections. Each of these dots is a single subject. We had 16 subjects. On average, across the 16 subjects, we do in the low 80% range in terms of being able to discriminate hits from correct rejections. And this is using data from not the whole brain, but much of the brain. And I'll skip over that point. There's a relationship between the classifier performance and the subject's behavior, memory performance. You can also train the classifiers off of local patches of brain data. And if you do this using local patches of 123 voxels, the classifier, I'm sorry, you can't see this. I think this is 65% or so. The classifier does reasonably well, even by being trained up on 123 voxels. Moreover, these classifiers, I noted that the classifier for each test trial is making a probabilistic statement, and so you could, with classifiers, you can assess the classifier's accuracy for all trials, or you can maybe want to assess how well does the classifier do when the classifier is more versus less confident, right? So you can set the criterion at different levels. And so here are all data, and then as we're moving to the right, we're interpreting the classifier's predictions for fewer and fewer trials, being more and more conservative, listening in on those trials that the classifier is increasingly more confident in its prediction, being a computer algorithm, forgive the anthropomorphism there. And as you can see, across 16 subjects on average for hits versus correct rejections, we can get up to 95% accurate. This was a bit startling to me in terms of how well it performed. Okay, what I presented to you thus far is the comparison of hits versus correct rejections. There's a confound or a conflation of true experience with the person's memory state, in that they're old items that are perceived as old, new items perceived as new. So what if we try to hold the objective experience constant? How well do we do? So here, this is a comparison of discriminating between hits versus misses. Both of these classes of items, these are faces that the subject saw. In one subset, the person recognizes or remembers having seen the face, and the other subset not. And the classifier's doing it, anyway, 75% correct. What about false alarms? These are false recognitions. These are novel faces that the person is perceiving as having been encountered versus novel faces perceived as novel. And the classifier is doing, again, about 70% here. And if you, again, look at, play with the classifier's sort of threshold, and only listen in when the classifier is more confident, you can get into the upper 70s or 80 percentiles for discriminating these sort of psychological states or the subjective experience of recognition versus the absence of recognition. The data, if you look at that where or how well the classifier does off of small patches, you can see actually that the information about subjective recognition is distributed throughout the brain, but it's distributed in ventrolateral and dorsolateral prefrontal cortex, in the anterior cingulate, in posterior parietal cortex. This map will look, I believe, a lot like the CRIST map that Dr. Lakin just presented to you for discriminating between putative lie versus putative truth states. And I'll come back to that. The other point to make is that, well, there's high similarity. There's maybe a sort of amplitude difference, but there's high similarity in where the information is for hits versus correct rejection, so true recognition versus correct rejections, and false recognition versus correct rejections. There's a common set of frontal and parietal regions that are relaying information about the subjective state of memory, and this is consistent with a lot of group average univariate fMRI and PET data. Including work from Dan's lab, Larry's lab, and other labs. Okay. The rest of the talk, the points go much more quickly. So point one, can we differentiate or decode the subjective memory state in the laboratory reasonably well here with this very restricted paradigm? Can fMRI decode a person's true experiential history, that is for items perceived as old? Can we discriminate? Thanks, Dan. Between true recognition and false recognition, and for items perceived as novel, can we nevertheless read out those that had been encountered versus those that hadn't? And so here, given the performance of subjects, we were able to look at a subset of our trials, those items that subjects made memory judgments where they had low confidence. Here, low confidence hits, old items that the person embraced as old, but they were only moderately confident or low confident. So this is true recognition, and here's low confidence, false recognition. Can the classifier discriminate between these states? What about misses versus correct rejections? And the classifier relative to reading out or interpreting the subjective state of the person, whether they're in the state of recognizing the stimulus is not as familiar or, as having been encountered versus novel, reading out the objective state of an item, holding subjective state constant, we do much worse. And even when you look, you only listen to the classifier when it's very confident, we don't sort of crawl. In one case, misses versus correct rejections, we don't crawl off of chance, really, and we only get into the sort of mid-60s for the other. Nevertheless, there's a rich literature on there being modest but nevertheless consistent differences in fMRI signal between true recognition and false recognition. Those differences are often in perceptual cortical regions where real experience has been hypothesized and there's behavioral data to support this, typically associated with perhaps greater perceptual detail. And when you look at this comparison here, true recognition versus false recognition, the only regions where we actually do even slightly off of chance, but not very well off of, not far from chance, are these perceptual cortical regions that have been previously implicated in the representation of visual faces. And this is consistent with the sensory reactivation hypothesis that when we remember, we're in essence, true experiences, we're replaying back the cortex or reactivating cortical regions that represent perceptual details about that experience, and that this degree of replay might differ between true and false recognition. So can we decode somebody's actual experience, holding their subjective memory state constant? Not very well here. Can we decode experience, true experience, when we're indirectly probing memory? So instead of, in the next experiment, having the subjects make explicit memory judgments, do you recognize having these encountered this face or not? We simply presented old and new faces and had them perform a completely unrelated task. They just indicated whether the faces were male or female. When we do that, we had 7 subjects. We are not significantly off of chance. So when memory is not being directly probed, we do very poorly in being able to identify which items from the brain patterns, which items the subject had actually encountered versus not. And this is just replicating that when you actually probe or ask them to make some statement about memory, we do well again. So this makes the point that retrieval processes are not automatically triggered. We've known this as cognitive neuroscientists for quite some time, but depend upon a participant's goal state. And it also suggests that simple countermanding or countermeasures might dramatically alter classifier's performance. Last 2 slides. Okay, so what is sort of my conclusion here? How well do we do this? This is an early study. We have more studies underway. Under some highly controlled conditions, fMRI can discriminate between whether someone is remembering or not. But we do very much worse in terms of reading out true experience. Under highly controlled conditions, fMRI can only moderately discriminate between true versus false memory or detect past experiences when the subject fails to remember. There's a whole host of caveats. We have no idea whether at the individual item and the individual subject level, whether we could identify the source of a particular memory. That is that the person is evidencing has a neural pattern that suggests memory. Is it because a person participated in the event, imagined the event, learned about it in the media? This is actually a statement in the Mabai case. The judge, the forensics expert said this brain pattern could only be present if the person was at the scene of the crime and participated in the crime. It's a very specific statement about the source of the memory. Countermeasures, I've already alluded to that, and there's already our data suggests that countermeasures might actually be a serious limitation here in terms of application. External validity, we're now looking at real-world autobiographical events. There's a whole host of factors that I think apply to and might have serious constraints on fMRI memory detection that might also apply to fMRI lie detection, issues of retention interval, practice over intervening time during that interval, the emotional significance, the motivation of the subject, the stress the subject's in under that time, possible group differences. Final points, fMRI memory detection and lie detection are often linked, and they can be directly linked, but nevertheless they also can be quite distinct endeavors. Lies are designed to deceive, whereas the work I've discussed, the subject's intent was to be as accurate as possible and not sort of to misstate their memory states and memory beliefs. These issues of fMRI memory detection, I think, do have some implications for fMRI lie detection. I highlighted the similarity between the CRISP meta-analysis map that Dr. Lakin showed you. My lab has actually replicated that map. I fully agree that there's consistencies across these laboratory-based studies of fMRI lie detection. We included about 25 studies. Thanks, Dan. It's 30 seconds. So we replicate that, but the question is, what does it mean? Many, if not almost all, of the studies that are conducted in the lab, and this is where lab versus real world, I think, does matter. Many of those studies might actually conflate issues of memory, stimulus salience, and attention with issues of lie detection. And so the fact that there's consistent observations across studies doesn't in and of itself tell us what those consistent observations are about. They could be about neurocorrelates of deception. They could be about neurocorrelates of memory, stimulus salience, attention. And I think there is more work to be done there. Thank you for your time. Your attention.
Time for a couple of questions.
Hi, Beth.
Hi, how you doing?
Great to see you.
I'm curious, you compare the low confidence hits and false alarms. Is that because you only had enough data to be able to do that? And if you could create an experimental situation where you had high confidence hits and false alarms, you think things would be any different, or still you would conclude only modest ability? I
think that that's a fundamental and important point. I don't want to overplay these data one way or the other in terms of being more promising or perhaps raising more skepticism. Dan has written about this, you've written about this. The neural correlates of false memory, there's not like a single sort of network there or single sort of pattern that's going to be a marker of false memory. It's going to critically depend upon what are the stimuli, what are the contexts in which the stimuli were encountered, et cetera. Here, the reason we did that analysis is we did not have many high-confidence false alarms. We now are doing a real-world sort of autobiographical memory experiment where Stanford undergrads are walking around campus with sort of digital cameras that are automatically taking pictures, sort of 30,000 pictures in 3 weeks. And they're encountering, so the sample is very homogeneous, and so we're thinking or we're hoping there might actually be an increase in high confidence false memories because they're sort of shared sort of context, but the details might differ. Our first pass on this is actually memory is even better than here, and our classifier performance is even superior than here, and we have very few false memories, period. But we're hoping to start to go down that route, and I think it's an open question, and you may well be right. As you push into the real world for particular kinds of contexts and kinds of stimuli, one might do much better.
Just one very quick question.
Hi.
I know that you also do work at the encoding phase, so even before you interrogate the subject's memory for the items that were encountered, do you think that and we know that the neural signature for items that will be remembered differs from the neural signature for items that will be forgotten. Do you think that at encoding, before you interrogate the subject's memory, that also the neural signature for items that are destined to be lied about? So at encoding, you witnessed an event and you intend to lie about it. Do you think that will differ from forgetting or not?
Well, there's actually two things that I think you had in your question. One is there something about the moment when an event is being encoded that's predictive of something in the future? And then I thought you were going predictive of true versus false memory, as opposed to intent to lie versus not lying. So, one, there is some work. Brian Gonzalez's work, Dan's lab has done some work here, looking at encoding predictors of false memory. This has to do with some of Beth's work on it, and others on imagination inflation. And there's some data that suggests that you could, not in this sense of prediction at the individual item level, though I think you might be able to get there, read out which items that somebody, say, imagined, which trials where somebody had an imagination for something that they didn't actually see or perceive are actually going to be later on remembered as having been associated with true perception. Okay, so I think we might be able to get there, but that work has actually not been done. The second, and this, I know I have to get off stage here, this issue about intent, I think it's actually an important question. All of the, and Dr. Lakin should see if you should correct me on this, all of the fMRI lie detection work that I know of, the lab-based studies that are published, are about statements after some event where the subject, the individual tends to be instructed to lie versus not, but there's statements about what actually occurred. In the Semerow case which went to the Daubert hearing in Tennessee, the questions, the facts of the matter weren't about whether he did or did not file these Medicare, I believe, or Medicaid claims. The question was about his intent, and his intent 7 years ago. And so these issues about whether we can read out intent in memory, as well as how that interacts with ability to know whether or not the person is being accurate, I think are complex and haven't been addressed yet. Thank you.
Thank you.